Welcome back to Basic Electronics. In our treatment of op-amp circuits so far, we have treated the op-amp as being ideal with no second order effects, so to say. A real op-amp shows slight variations from the ideal behavior, and in this lecture we will look at two such non-idealities, namely offset voltage and bias currents. We will start with the offset voltage, look at its origin, and then learn how to represent the offset voltage with an equivalent circuit model. We will also look at the effect of the offset voltage on the performance of two of the circuits we have studied earlier, namely the inverting amplifier and integrator. We will then look at the offset null arrangement in the 741 op-amp. Okay, so let us begin. So far we have been talking about ideal op-amps. We now want to look at some of the non-idealities in practical op-amps, starting with the so-called offset voltage. Let us see what that is. Here is an op-amp, and here is the VO versus VI relationship for the op-amp. Note that the scales are different. This is millivolts and that would be volts. Typically this would be like minus 10 volts, that would be plus 10 volts, something of that order. And as we have seen, this part here is the linear region of the op-amp, and this one is the saturation region. And the slope of the VO versus VI curve in the linear region is of course very high. That represents the open loop gain of the op-amp, and for the 741 it is something like 100,000. For an ideal op-amp, the linear region would actually go through 0, 0. That means when VI is 0, VO would also be 0. But that is not what happens in a real or practical op-amp. For a real op-amp, this situation is more likely, something like this. And we notice that this linear region is now shifted with respect to 0 by a certain voltage. And this is because of something called the offset voltage. Now let us see where the offset voltage is coming from, what its origin is, and then we will see how to represent it. Here is the internal circuit of the 741 op-amp, which we have seen before. This is the non-inverting input terminal, that is the inverting input terminal. Now ideally Q1 would be the same as Q2 in all respects. Q3 and Q4 would be the same, and Q5 and Q6 also would be the same. And when V plus and V minus are made equal, then because of symmetry the output voltage would be exactly 0. Now that is not what happens in real life. In reality the transistors would be close but not quite identical, and there would be small differences between the two, and therefore it gives rise to the offset voltage. That means the VO versus VI curve gets shifted, as we have seen in the last slide. Okay, let us now see how to represent the effect of this offset voltage. This is our ideal op-amp. This is our real op-amp. Now in the real op-amp model we have this box here, which is actually the ideal op-amp, and on top of that we have this voltage source here. Now this voltage source represents the effect of this offset voltage. It's called VOS. So this is the same model as we have been using, no offset, and the real op-amp is represented by this combined model. We now want to figure out the relationship between this voltage here and VOS. So let us begin with an equation which describes VO in terms of V plus and V minus of the real op amp. What do we know about VO? We know that VO is AV times the difference between these voltages. So what is this voltage? It is V plus of the real op amp plus VOS, that quantity. What is this voltage? It is V minus of the real op amp, like that. Now we want to ask the question, for what value of VI, this VI, will VO be 0? And that will give us this VI here, for which VO is 0. So all we need to do now is to put VO equal to 0 in this equation. Then we get V plus VOS minus V minus equal to 0. This equation here. What is V plus minus V minus? That is VI. So therefore we get VI plus VOS equal to 0, or VI equal to minus VOS. Now in this particular example, VO is 0 when VI is something like 1.5 millivolts, and that is minus VOS. So VOS for this particular op amp is minus 1.5 millivolts. The sign of VOS is not so important, its magnitude is really what we are concerned about. Let us now look at some typical numbers. For the 741, the offset voltage is something like 6 millivolts or smaller in magnitude. And for op 77, VOS is much smaller, 50 microvolts. So clearly op 77 is much better than 741 in terms of the offset voltage. Let us now look at the effect of the offset voltage on an inverting amplifier. Here is an example. R2 is 10K, R1 is 1K. So the gain of this amplifier is minus 10K divided by 1K, that is minus 10. This is our real op amp now, and so we replace that with the model that we have seen in the last slide, this model here, which consists of this part, which is the ideal op amp with no offset voltage, and a voltage source which represents the offset voltage. Now how do we go about finding VO in this case? The easiest way to do it is to use superposition, because we have two independent voltage sources, VI and VOS. Note that VOS is not really a voltage source in real life, but as far as circuit analysis is concerned, we can surely treat it as a voltage source, and therefore we can use superposition. So by superposition we get two contributions. This first contribution is when VOS is 0 and VI is kept as it is, and that is simply our good old inverting amplifier with a gain of minus R2 by R1. So that is the first term. The second term represents the effect of the offset voltage. So we keep VOS and deactivate VI. That means we ground this, and then we see that we have VOS here, and R1 is going to ground here, and therefore the circuit looks just like a non-inverting amplifier. And we can use the expression that we derived for the gain of a non-inverting amplifier, and the output voltage would be VOS times 1 plus R2 by R1. So this part here is the contribution from VOS. Now in this case, let us take an example. Let VOS be 2 millivolts. Then this would be 2 millivolts times 1 plus 10K by 1K. So 1 plus 10, 11 times 2 millivolts, which is 22 millivolts. So the output voltage would now show a shift of 22 millivolts because of VOS being non-zero. Let us consider an integrator circuit now and see how its performance is affected by a non-zero offset voltage. Here is the circuit. This is a real op-amp with a non-zero VOS. So we replace that with this model here. Once again, this part is the ideal op-amp, and the effect of the offset voltage is represented by this voltage source. Now for the ideal op-amp, we know that V plus and V minus are nearly the same. Since V plus is VOS, V minus is also equal to VOS. What does it mean? That means this current I1 is VI minus VOS divided by R, that equation. And because the input current of the op-amp is 0, that current will also go through the capacitor. And therefore we can write I1 equal to C dVC dt, and we get this equation here. In other words, the capacitor voltage marked here is given by Vc equal to 1 over Rc integral of Vi minus Vos dt. And now there is a problem. Let us consider the simple case when Vi is 0. What do we get then? We get Vc equal to 1 over Rc integral of minus Vos dt, where Vos is a constant voltage, however small. Now because of this relationship, what will happen is Vc will keep on rising or falling depending of course on the sign of Vos, and eventually the op-amp will be driven into saturation. And that's a perfect disaster. We definitely want to avoid that kind of situation. And therefore we definitely need to address this issue. We need to do something to the integrator circuit so that this does not happen. Here is an improved integrator in figure B here. And what is the difference between these two circuits? We have a resistor R prime connected in parallel with C here, and we will see how that helps. What we will do is we will consider both of these circuits, our earlier integrator circuit and the improved integrator circuit, with Vi equal to 0. So this node, which is otherwise equal to Vi, is grounded in both cases. And now let us see what happens in each of these cases. Case A, the non-inverting input is at VOS, so therefore V minus is also equal to VOS. I1 is equal to VOS divided by R, and therefore this current is also equal to VOS by R, and that current is minus C dVc dt. So as we saw before, Vc is then minus 1 over Rc integral VOS dt. Now this integral will keep rising if VOS is positive, or it will keep falling if VOS is negative. In either case, the op-amp will saturate, which is something that we definitely don't want. Let us now look at case B. In this case, there is a DC path for the current, this path here, and in steady state there is no current through the capacitor. It's an open circuit, and the circuit looks just like a non-inverting amplifier with input equal to VOS. So therefore the output is going to be VOS times 1 plus R prime divided by R. So the op-amp would not saturate. Let us make a few comments on R prime now. R prime should be small enough to have negligible effect on VO. For example, if we make R prime equal to R and VOS is 1 millivolt, then this entire VO would be 2 millivolts, which may be small enough, and we would be probably willing to accept it. That is one consideration. Second, R prime must be large enough to ensure that the circuit still functions as an integrator. For example, if we have a square wave applied here instead of grounding it, so the input voltage Vi is actually a square wave, then we would expect a triangular wave at the output. That is the function of the integrator, as we have seen before. And if our R prime is small enough, then the functionality of the integrator itself would be disturbed, and we certainly don't want that. So what does it mean in terms of frequency domain? We want the impedance of R prime to be much larger than the impedance of the capacitor, which is 1 over omega c in magnitude. So at the frequency of interest, we would like to satisfy this condition, R prime much greater than 1 over omega c. If we do that, then this circuit B will do our job. The op amp will not saturate, and what we will see is a DC shift at the output given by this voltage here. So with the square wave input, instead of making Vi equal to 0, we apply a square wave here. Our output now will still be a triangular wave, as we would expect, with an amplitude which is determined by the component values R and C and the period of the input waveform and the voltage values of the input waveform. And in addition, we will only have this small DC shift at the output. So our basic functionality is retained, and we will only see this additional shift at the output. In some op amps, there is a provision to nullify or minimize the effect of the offset voltage, and that arrangement is called offset null. In the 741 op amp, for example, these two terminals are brought out as pins 1 and 5 of the IC, and the user is supposed to connect a pot between those two terminals with the wiper connected to the power supply minus VEE. To nullify the offset voltage, what the user does is to connect the non-inverting input and the inverting input together, let's say to ground, change this wiper position until VO is made 0 or as small as possible. Let us try to understand what is happening when we change the wiper position here. What we are doing is connecting in parallel with R2 some resistance, and connecting in parallel with R1 the remaining resistance of the pot. So essentially we are changing R1 and R2 when we change the wiper position, and that helps to restore the balance between currents in these two branches, eventually reflecting at the output. So this offset null facility is indeed a very useful facility, and it is particularly relevant in applications where we cannot tolerate a DC shift that results from an offset voltage. There is another non-ideality that we need to consider for some applications, and that is the input bias currents. What do we mean by input bias currents? At the non-inverting terminal, we have this base current going in. At the inverting terminal, we have this base current going in, and these currents are called the input bias currents. Now, when we analyzed circuits, we said that these currents are small because they are base currents of transistors, and they are definitely much smaller than the collector currents, and therefore we have been ignoring these currents. But they become relevant in some applications, and let us now see how to represent the effect of these bias currents with a model. So here is the model that we can use to represent the input bias currents. This is the overall real op amp which has non-zero input bias currents. This rectangle here is the ideal op amp which has no bias currents, and the bias currents are external to this ideal op amp, and they are represented by these current sources. So what do we see at the non-inverting input? We see this current IB plus going in, and we also see at the inverting input this IB minus going in. What it means is that this ideal op amp still has zero input currents, and with this equivalent circuit we can represent the effect of the input bias currents and also analyze circuits in a simple manner, because we can use all the features of the ideal op amp in circuit analysis. It turns out that IB plus and IB minus are generally not equal, and we therefore define two additional quantities: bias current, denoted by IB as the average of IB plus and IB minus, and offset current, denoted by I sub OS as the difference between IB plus and IB minus. Let us now look at some typical numbers. For op amp 741, IB is 80 nanoamperes and IOS is 20 nanoamperes. So the offset current is surely much smaller than the bias current, in this case a factor of 4 smaller. For op 77, IB is 1.2 nanoamperes, much smaller than IB for 741, and IOS is 0.3 nanoamperes. Op amp 411, which is a FET input op amp, IB is even smaller, only 50 picoamperes, whereas IOS is typically 25 picoamperes. So there is a wide variety of op amps available in the market, and we need to make a judicious choice depending on our application. To summarize, we looked at the meaning of offset voltage of an op amp and an equivalent circuit to represent it for circuit analysis. Using this model, we looked at how the performance of an inverting amplifier and an integrator is affected by the offset voltage. We found that for the inverting amplifier, offset voltage gives rise to a DC shift at the output. For the integrator, the effect of offset voltage is more serious, as it causes the op amp to saturate. We looked at how to correct this situation. We also looked at the offset null arrangement in the 741 op amp. We have then started with the input bias current of an op amp, and we will continue with that in the next class. So see you next time.